Okay, you're alive. Hi, folks. I am exhausted today. This is the end of week 3 of a borderline batshit insane cut, probably averaging over 1,000 calorie deficit a day. Running average now 40 miles a week. And lifting 5 days a week, including deadlifts every day. On top of that, we've been doing hard research all week, a bunch of random meetings as well, which I just got back from a couple of. So, here's what I want to do today. I don't really want to go work on any of the existing fancy algorithms and changes and such. At least not for the next couple hours. I kind of just want to have some time to sit here, take a step back, and think about where we are algorithmically. Welcome. Hey, Weston. Let me just open a Google Doc. Right? That's pretty much the long and the short of it. I'm writing this off the top of your head. How many params do you think a basic feed-forward neural net would need to be to predict the location of the second mass? 2 seconds. 2 seconds. You have to be sure that you actually have like forces and stuff, like velocity and stuff, if you don't have memory to do that. I don't know. I would start with like our basic default network architecture, though, Weston. Start with the basic architecture we have. 128 hidden. Like 100k or whatever. It's tiny. I suppose the expectation I have for world models is quite high, right? You probably just need to take a lot more gradient steps on the world model. Architecture as well. All the existing methods are set up this way. Too deep, Weston. Too deep. Two hidden layers. Observation. Activation hidden. Activation hidden. Activation output. That's way too deep. Classic rookie mistake. Actually, the efficient zero objective is not like the dreamer objective, right? Is there a reconstruction objective in this? I don't think there is, right? Yeah, there's no reconstruction. So I think we're gonna say no. At least not recon. About something like this. Dynamics is gonna predict. The thing is, it predicts the next state embedding, right? This is a hard thing to learn. See, this is because this is a moving target, right? You're predicting like your next embedding. Finally, a new topic. Hang on. America's pretty damn good, as it turns out. If you just shut off the news and actually live here, it's pretty good. What are we working on today? Some thoughts. Some thinking about RL. I think we're gonna end up doing some math. So, hang on. Where's the derivation of this thing? I thought it's here, isn't it? Here it is. It's here. I'd like to understand precisely why you need to have, like, to what extent the on policy assumptions coded in, right? Exactly what is this? Ah, I see. Oh, hey, that's Will. What are you linking me to? What is this? What are you linking me this for? So, Will, the thing I'm trying to figure out at the moment, I kind of don't think world models are the end-all be-all. I'm trying to see if there's some way we can keep the on-policy formulation, like that objective formulation, but incorporate old data somehow. So basically what's happened from the last couple weeks of research is you kind of can't take off-pol or world models or anything and get like a single algorithm in which you can spend more compute or you can spend more data, because there's a massive compute gap between on policy and then either off-pol or world models before something works. Like, on-pol's the only thing that actually works at the moment consistently. What am I looking at here? The plan for today is to kind of just hang out and look at some math and to think about things. Been a pretty tiring 3 weeks, and I kind of just need some time to step back and think about stuff on this. So if you're interested in like how do we actually very deeply think about these algorithms and what to do with it, in the right spot for that. The thing that I don't understand here, why can't you just apply this bloody thing to... Okay. Log prob. I still don't understand why it is that this implies why this is an on-policy derivation. Like, why can't I just recompute the probabilities under a different policy? Yes, there are not multiple open AIs. Does anybody, like, okay, obviously, yeah, this is a simple derivation, right? This is a pretty simple derivation. But the thing I don't understand here, why can't I use a policy that is different from the one that's produced the trajectory here? Working on the N. Enjoy learning. You're good. Wait, is it... Probability of... Is there a way to cover the previous videos? To cover the previous video? Yeah, they're on... All the VODs are on YouTube. Trajectory is now unlikely. Right, but what I'm trying to figure out is, like, why does that matter? Okay, like, here, consider the following scenario, right? Let's say that you have a bunch of trajectories that come in from, on policy, like, just come in from the current policy, but then I just add in some expert trajectories, but I don't tell you which ones. Right, so you have some perfect, so-called perfect trajectories. According to this on-policy assumption, you shouldn't be able to use them, and according to my tests as well, it seems that this messes up the algorithm. This seems like a really bad property for an algorithm to have. And I'm resisting the urge to start typing crap into LLMs because they're just going to give me, like, I don't know. I've tried this specific topic and you just get a lot of circular, really, like, dumb, entrenched thinking. I mean, this first line very clearly, where's tau defined? Maximize the expected return. What is tau? Oh, tau is sampled from pi of theta. Okay. Okay, trajectory is... We aim to maximize the expected return. It's sample reuse. So the idea is, if you're just getting on policy segments, you have very little ability to learn from them, and like you can't even keep around your best examples, for instance. Like you can't even keep around good segments from before. Like lucky segments, for instance, you can't even keep them around. Once you've used them once, you're already off policy. Technically, you're immediately off policy, right, at the second mini batch. So you're able to learn a very limited amount from the data. Right, but so this is what I'm trying to figure out fundamentally, like... Okay, this objective, it's already encoded at the objective here, right? Because this is... You're trying to maximize the expected return with a trajectory sampled... This is not what you want. You want... How would you write this? Okay, so this objective function immediately has this encoded. But I don't think the whole derivation does. So the probability of a trajectory, given that actions come from pi theta, okay, try to use less layers, then I need more total params. Are you using the puffer implementation, Weston? Like, I get the desire to do everything custom, but the thing with RL, Yeah, so here's the problem with RL, okay? It is really, really brittle, and it's not going to make any bloody sense to you if you have a custom implementation that's not actually tested to be stable over a wide range of problems. Like, this is not the equivalent of, like, let me go implement my own cool render algorithm or, like, my own cool, like, domain-specific whatever. It's like, RL is actually genuinely and truly an area where just getting the basic algorithms to work is non-trivial. Like, very non-trivial. To the point that, like, I would not be confident that if I spent a day implementing any algorithm from scratch on your problem, given a correct version of your environment, I would not be confident I could get it to work. That should tell you a lot. Okay, I think... So this formula is valid whether the actions come from theta or not, right? This is just saying how likely you are to see a trajectory. Wait, does it? What does pi sub theta give you? Is it giving you a probability distribution? Yeah, this is a log probability, right? And then... Okay, and I think this is still valid. Is this gradient not still valid? Can you hint what the problem you're in today? Yeah. So basically, Satcha, I'm trying to understand exactly where and how policy gradient algorithms depend on the data actually being sampled from the current set of parameters. And the hope is that I'm going to be able to figure out new ways of leveraging old data without having to dramatically modify the policy gradient setting. Gradient of the log prob of the trajectory. Isn't this true regardless of... This is true regardless of where your data comes from, right? This step 5? Because this is just like... It's done in log space, right? But this is basically just saying that the delta of a trajectory is the delta of each of the actions taken along the way. So if you want to increase the probability of a trajectory, right, you increase the probability of taking each of the actions. That's like completely trivial, isn't it? And this is basically... Isn't this the behavioral cloning objective exactly? Does anybody have a good... Does anybody have a good reference to the math? Like, you can write behavioral cloning as log prob, right? Actually, I can get this at least if I don't give it any other, like, context. I should be able to, right? That I can probably get and I can compare. If anybody has an actual reference, that would be better. But I think that you just do this, don't you? Over n log prob action given state. Yeah, so this is identical, right? So this is what I was getting at before. So this is literally this core piece of math here from policy gradients is behavioral cloning. Is the policy gradient a gradient? Drop the discount from the state distribution. The objective differs in a way where data comes from IID or Markovian data. If you have specific things that I should look at in this, please tell me, because otherwise this is a lot of math. If there's not a specific point. I have a somewhat broader problem with this at the moment. Expectation of scoring data function weighted with trajectories. Expectation of scoring data function. Is that form there's no reward. Yeah, so in this formula, this is not the full derivation, right? This is an intermediate step of the policy gradient derivation. But the thing is that this portion is exactly equal to behavioral cloning. Like, this is the behavioral cloning objective. Right? This says that if you want to make the policy behave in a certain way, this is how you change the action distribution to match. It is, but the data does not have to be Markovian. Okay, that is true. But, like, this objective here, right? The thing that bothers me is this objective is literally behavioral cloning objective weighted by return. That's literally all it is, right? That's policy gradient. Behavioral cloning does not require anything. It doesn't require the data come from the same policy either. But somehow weighting that data by the return, now suddenly it's required to be on policy. And I don't understand that. Like, yes, right, I understand that this objective here, this is written as trajectory sampled from the current policy, right? So this objective at the top, this encodes that the data has to come from the policy pi, but this portion doesn't. This is just behavioral cloning, and then the final result is behavioral cloning weighted by return. Do you see what I mean? Now, I suppose that there is like one major confounding factor here, right? This is not actually the algorithm that works in RL. Teacher policy is very different. No, Damator, it doesn't, because you don't need to have a teacher policy, you just have to have a data set. Behavioral cloning, you can work on any distribution. It's that way because you need to maximize the cumulative return, which implies you need to weight it with the likelihoods. You're doing the reasoning in the wrong direction. Well, can't you do it in either direction, though? That's my point, right? Because you can set this objective to 1, and then you have behavioral cloning, agree? Like, you set this to 1 and you just get behavioral cloning, and behavioral cloning is very effective. There's one major conflating factor here, though, right? Which is vanilla policy gradients doesn't actually work, right? This is and I hate that this is true because this is such a mess. Why is this doing this? Stop, what is this new stupid Chrome feature? Go away. Okay, so here, what problem do you solve? You solve behavioral cloning, Satya. So if you have an existing set of good actions in state, then you get a policy that actually does that. I got 19.5 on Pong after making one. Such luck. Yeah, I'm doing something a little different, Spencer, at the moment, because the thing I don't know, I think the world model direction is still potentially good, and the reason it's good is it takes very good advantage of the hardware, but it's not going to give us, like, a smooth... I could be wrong, but I don't know if it's going to give us, like, a smooth transition between low data and high data. I think it's, like, more of a, you have to invest a ton of compute to match results, and then you invest even more compute and do better. Maximize return, which defines the... Okay, Satya, but, like, here's the thing. If I just do vanilla RL, and instead of sampling the data from the expert, like instead of sampling the data from the current policy, I just give you data from an expert, it breaks, right? So weighting the data by return, it actually breaks. It means that even if you have ideal data, you can't learn from it. The world model part of your policy loss was 0 because it was no longer tracking previous log probs. So the reason for that, Spencer, is the previous log probs are the log probs at the time that you're collecting the data, right? But because you're hallucinating new data, it's perfectly on policy. Like, there's no gap. The only thing that you could do is if you wanted to track a loss like that, you could track after the update and before the update, but then you'd have to do an additional forward pass to even do that. So, like, they're basically, it should just be 0. The previous log, like, it should be 0 because it's fully on policy, right? Unless you're doing an extra eval afterwards. Gradients from imitation learning to be much larger than vanilla RL. Well, you're gonna tune, I don't know why they would be. You're gonna tune your algorithm regardless, right? Like, you're gonna just tune hypers to the problem regardless. It depends on the scale of your returns, actually, is what it is. What mixture of Gaussians, man? What mixture of Gaussians? Dreamer has this. Oh, that's the old form, right? The one in Dreamer is, and this is in the Dreamer branch implemented. It's 32. You come up with like a 32 latent vector, and then you sample 32 different categoricals from it. It's weird. I think the idea of all these things is that you end up with a stochastic representation. You're free to play with it. I'd be shocked if that's like, yeah, if you just do that, then you optimize the world model so much faster that you don't end up with problems. The world model direction is useful though, in the sense that like, if you think of, if we're doing stuff on the higher end chips, right? It's like a purely on device online RL. Stochastic part. Okay, but like the env is not even stochastic, Spencer, right? Like, the imagined rollouts are still stochastic because you're sampling from the policy, and the policy is stochastic. It's just the transition dynamics that are not stochastic, and we're testing it on simple-ass environments that are not stochastic. Spawning per Pong round. Okay, so the other thing that I didn't handle here is you're supposed to cut the trajectories when the world model predicts the done signal. You're supposed to cut the trajectories off. Vectorize it towards the expert data. Okay, but this is not my objective either, Satya. My objective here, right, is in one algorithm, you should be able to learn from either expert data or like online data. You should be able to learn from mixed quality data. If you have an offline RL objective that you think is good, then go ahead and show it to me. But if it has like a very short form bootstrap, or if it has important sampling, it's probably crap. Like, as far as I've seen, you need the long form bootstrap. It usually has a lot of that. What, short form bootstrap or important sampling? Yeah, so that just screws you. That just basically means your algorithm sucks. Advantage weighted. Yeah, so there's advantage weighted regression. I messed with some stuff like that a little bit. I could probably take another look. The problem is the experiments there. Like, they don't have experiments from that are actually useful. It's all this control crap. You reuse data until the advantage gets smaller. Yeah, so I was trying to do that, Spencer, but it does seem to be the case that the current form of policy gradient, like, it really wants your data to be on policy. You can't just keep reusing data until the advantage gets smaller, because it gets to be very off policy. I tried that. All of it. Okay, actually, this was something I saw yesterday. It's for frickin' LLMs. So this is just, I think I looked this up yesterday. So this is basically just like smoothed important sampling, right? Yeah, this is just smoothed important sampling. Well, you can't forget about LLMs because it basically means you may as well just assume this has no usable experiments. It works on LLMs is not good evidence. Like, LLMs are baby mode RL. Probabilistic inference. Yeah, but like both, okay, just having a big KL div and doing important sampling are both just saying, let's not actually use the training data, right? You can't just give me an objective that's like shit compared to the on policy objective and be like, ah, good, now we can do off policy, right? It's like, no, if the objective is shit by comparison, that doesn't help. We need an objective with a reason to think that it's actually as good as the on policy objective, right? See, like, this is useless, okay? Why is this useless? Because this basically just says, hey, if the trajectory is unlikely under the current policy, throw it away. So basically, you've just written a piece of fancy math that does the exact same thing as just not using your data. So that's useless, right? Like, the only thing that's salvageable about this is that if you're keeping around, say, some really good trajectories that have low probability, then eventually, if the policy gets good, then you can use them. But, like, this is not helping you actually get there. This is a bad algorithm. Lower bound of samples required to solve an env. I guess, Spencer, like, you can do that, but the problem is you're going to end up just going and collecting, like, cherry-picked baselines from a ton of different papers if you do that, with, like, no respect to compute. The thing that I actually want to have is I want to have a reasonable compute data trade-off curve. See what Satcha's linked to me. Offline RL for online. Offline RL for online RL. What? Online algorithms off policy. PyTorch is printed, bringing Moo on. That'd be nice. Is it possible to do transfer learning with some hard-coded player script? Yes. Yeah, you can do that, Tim, but that's not exactly what we're trying to do. Not policy gradient, I forgot. What online algorithm do they have that's not policy gradient based? This is also weird in that it's like targeting exploration stuff, which is probably like one of the lowest quality lit areas in RL. And that's saying something. That's Q-based, I see. Sarsa, yeah, we're not dealing with that. If they have the original GAE paper do. Nah, they don't. They just do their own. What should optimally happen? Just choose or to compute or data. So Spencer, the cool thing about that is if we do it right, we literally shouldn't have to because you just optimize for wall clock time. And then the simulator is running at whatever speed the simulator runs. And then it'll just use more compute if it needs to. And you can do that right now with Puffer, but the thing is, like, to be fair, I haven't tested, but there's no reason to expect Puffer as it is now to be able to scale well with compute, like, at all. It really just scales well with data. Use a restroom real quick. I'll be right back, guys. Wait, what? Overall takeaway for important sample is to make sure in policy won't differ much between time steps. That's not quite true, because important sampling, it will, if a piece of data has low probability under the current policy, it'll weight it as 0. So it's like, it will literally just weight it as 0. Multi-level Monte Carlo. So Satcha, the only thing I can see this mapping onto in RL is search, right? Like, this maps onto search, basically. You don't have, like, iterative refinement otherwise. What's the typical bottleneck on RL? More focused on hardware? Well, it depends in what approach, right? With our current stuff and our current sims, it's pretty balanced. If you get a slow simulator, then you're going to be bottlenecked by the simulator. And if you have a really fast simulator, then you're bottlenecked by the policy. It was weird to me when people go like, oh yeah, it's going to be high variance because it's a Monte Carlo estimate. It's like, literally that just means you have a bunch of samples and you average them, right? Can I link a paper? Yeah, you can link a paper. If X lets you link it. How do you spec a system for RL? At the moment, we have two different machines. We've got like high-end desktops, which generally have a very nice core to GPU ratio. Like, you've got a good number of cores to saturate the GPU, and then we've got tiny boxes, which are 32 core, 6 GPU machines, and those only are useful for the faster environments, because otherwise you can't keep up on the data generation. All right, let's see what you've got here with the map. Multi-level for average reward RL. Okay, I mean, if this actually, like, this would be cool if it works. Huh? How the heck do you do that? Okay. I'm trying to see how the hell you say that you can correct an optimizer for RL. Did preliminary experiments, right? Hmm. Can you explain to me how this is supposed to be... Gotcha, can you please explain to me how this is supposed to be low variance? So the problem with average reward anything, right, is that you're predicting average reward on next step. And while I would absolutely love it if I did not have to roll out trajectory segments for like 64 steps to make estimates, the reality is that rolling forward that number of steps actually lets you see what happens in the environment, right? If you actually follow the policy, so you don't have to estimate what happens in the future, you just know what happens in the future, right? Skip connections. Skip connections are good, Weston, but you should not be doing... You should not have deep enough architectures that should matter. No, I mean, this is good. Do you have any explanation as to, like... Because I don't... Okay, you have it, like, average reward is a unbiased objective, right? But I don't see how the heck you can predict that without the variance reduction of actually rolling forward. Like, the key thing, right, is that pretty much generalized advantage estimation is the actual workhorse that makes on policy RL work. Because you get, like, a really good estimate out of it. See if I can understand what the heck you've done mathematically here. The algorithm actually rolls forward, okay. Then how's it average reward? Oh, I guess you can still roll forward. Okay, yeah, you can still roll forward, I guess. Yeah, you can still roll forward, but you just have the, you don't get the same variance reduction, right? Doesn't use samples to update. Update the policy to correct the gradient. Correct the gradient. Markovian advantage. Markovian atom. I have no idea what this does looking at it. Five. Okay, what does this do? G is... Where's G even defined? Okay, G is equal to 2 to the negative J. D inverse. B is the matrix. Theta Z. Yeah, I've got no idea what this is doing, Satcha. This stupid thing here is the only reason RL works. We end up doing 16 core. It depends on your environments. The thing is, the Threadrippers are super expensive, so we do like 9950X. Estimation of the objective over the batch rolled out into the future. And you did this... Okay, so you put this advantage into the optimizer. In AI and robotics. They don't have degrees in AI and robotics that don't, like, aren't based in computer science. Well, maybe robotics you can have, like, a different engineering basis. There's no, there's no, like, degree in AI that isn't computer science core. Tried? I know, it's like, I can't even evaluate this, man. This is more math than I know. If you think that this is like, if you think that this works, though, I mean, you just have to you'd have to push the experiments, right? Like, the cool thing with Puffer is everything is so fast that if you write your optimizer, you can very easily do a lot of experiments on this. What would you go with? I mean, just core CS, right? So I guess the problem with computer science is like, it's kind of half a degree because it actually doesn't teach you how to be a decent programmer. And like, you really can't do much in CS if you're not a decent programmer. I mean, I have all of my advices on X. If you just check my X page on the articles tab, I have several guides for new people. Method computes estimations of the objective over the randomized batch rolled out into the future. Randomized over the randomized batch rolled out into the objective. Estimate the objective over the randomized batch out into. Isn't this what you do with Isn't this what you do with just like any of these methods, Satcha? Just not in the optimizer? Like, you do this with advantage estimation, right? Into an IIT. I don't know. I don't know why you'd ask an American. J is a random variable from June. Okay, let me see if I can actually. Roll this out into the future. Due to the negative J B inverse. This is the index? Heck. What is the special thing about putting the advantage calc into the optimizer? But for the gradient of the policy. Monte Carlo estimates not for advantage, but for the gradient of the policy. Wait, but Monte Carlo estimate, as it's meant in RL, literally just means averaging over different trajectory segments, right? Monte Carlo estimate is used. Or are you talking about rolling forward in a single segment? Proven AI as a finance student? I have my guides on X if you want all of my advice in one spot. The as a finance student part is not necessarily super relevant. Like, either way, you need strong CS, strong programming background, at least a little bit of math. As you can see, I don't have a ton of it. What the heck does you mean by... What do you mean Monte Carlo estimate over a single segment? You mean that somehow you're reducing the gradient? You're somehow reducing the variance of the gradient by looking forward over the data from the same segment? Like how? Wait, that's what advantage does, isn't it? Isn't that what advantage does, though? Isn't it? Like, this is also what advantage does, unless this is somehow getting distributed differently over the weights or something. Another estimator. I I haven't looked at Atom in a while. Is this G estimate, this G and this N, these are the main differences? I don't understand this, like, this whole framing. Stability hinges upon a hypothesis that the data generating process mixes exponentially fast with a rate parameter that appears in step size selection. What in the hell is that? Hey, how's it going? The hell does this even mean, mixing time? Close to its steady state distribution. What steady state distribution? There frickin' isn't one. These are not like steady state processes. What are you doing being confused by math? Recover the stationary. There isn't one though, right? Huh? A stationary distribution? Do you mean steady state? Because there isn't one. Doesn't seem like math. But Satya, there isn't a freaking steady state distribution, right? This is not like a pendulum or a process that you're monitoring for when it converges, right? It's an environment. It's an interactive process that changes throughout the entire course of the simulation, finishes, and then gets reset. Or even if it doesn't reset, there's still not a steady state. It's constantly evolving. Right? Like, this is why I get so confused with these works, because it's like you've gotten so far away from the problem that you're studying that you're just thinking about MDPs and stuff. It's like it doesn't even remotely, this doesn't remotely match the actual problem of learning in an interactive environment, right? Like, many existing RL methods employ stochastic gradient iteration whose stability hinges upon a hypothesis that the data generating process mixes exponentially fast. How the hell does it hinge on that? Am I supposed to understand any one of the big worlds? No, and I don't necessarily know if authors do either. Because this basically, at least as far as I can tell, and I can be wrong in this area, right? But like, this I want to understand more. This sort of language here, I don't see how this is applicable to the process, right? This is like so deep in the formalism. Like, this is not the thing that I'm concerned with here, right? The thing I'm concerned with is something that's substantially more grounded, which is that this derivation of vanilla policy gradients is literally return-weighted behavioral cloning. This is behavioral cloning. This is the discounted sum of rewards. So this is this formula. This is the core of policy gradient. This weighting prevents you from leveraging past data, is one way of interpreting this. And then additionally, you actually need advantage estimation. You need generalized advantage estimation for RL to even work. Am I interrupting something? Not particularly. What I'm trying to do today is I'm trying to piece through a bunch of stuffy formalism around RL, because the simpler doc is here. What I've found over the last few weeks, so on policy, which is what we do in PufferLib, is the only thing that just works. It works really well. It works really fast. You need to have a lot of data, though, and it doesn't scale great with compute. It scales really well with data more than anything. In off policy, it seems like the algorithms are fundamentally worse than on policy. It seems that they're like fundamentally worse because they do credit assignment over very short horizons, basically. And then they rely on you just running a ton of compute on them to make it as good as on policy, and then you can keep running it and do better. World models do basically the same thing. The results are better here, but more complex. X cut all of my messages. Great. I mean, if we consider... But viewing this as behavioral cloning isn't even super helpful, right? Looking, figuring out whatever that is. Well, what I'm trying to figure out is I'm trying to figure out... The simple version, right, is I'm trying to figure out how to make reinforcement learning scale either with compute or with data more smoothly. Instead of what we have now, which is Puffer's really good with a ton of data. There are other methods that work with a ton of compute, and there's nothing in between. Hello, welcome. I mean, this is the core right here, right? But saying this is the core is almost ridiculous, isn't it? This is literally just a formula that lets you... This is literally just like moving probabilities up and down. Well, it's moving log probabilities up and down. Same thing. Leveraging offline data, you need to make the policy aware of the expert policy. Applies important sampling or necessity to correct gradient steps of the necessity to correct gradient steps of the update. Yeah, basically I'm saying, are we sure that... But my question, Sacha, is are we sure? Are we sure that's the only thing we can do? This. Book is it? This is not a book. This is advantage weighted regression paper. If you won't regulate the policy update, the process diverges. That's what motivated trust region methods. But that's not the way that I want to address that, Sacha. Because trust region methods, all of them, it just says don't move the policy too much. That's not what we want, right? Don't move the policy too much just means don't effectively leverage your data. I looked at this thing before. I forget what problem I had with this. What are you teaching, sir? This is not teaching. This is research. This is live research on reinforcement learning. I'm a scientist and engineer. I stream all of my work on advancing reinforcement learning. Yeah, so I've seen VMPO. I don't understand how this paper is good because can you explain to me how this is supposed to be good when this is billions of steps for breakout? This is 8 billion steps for breakout. So I actually don't understand this algorithm. Like, apparently this is Google's better PPO or whatever, but, like, I don't understand that in the context of this result. Optimization is very different. Want to learn CFD? Could you suggest? Reinforcement for material. Oh, okay. You probably saw my stuff from reinforcement learning on material science. That's a bit different. I'm not a material scientist, right? I'm a reinforcement learning researcher. You'd have to ask. There are a couple material science people around in the Puffer Discord. I have materials on reinforcement learning. I don't have materials on specific application areas. Poses the same problem as I do. Well, then it sucks, doesn't it? Because look. How is this good? Like, you shouldn't need this amount of compute or this number of frames for this problem. Did you share the Twitter post you made for new folks? The article? Yeah. Let me grab the article. I guess there are two of them, right? There's the programming in ML one. There's the programming and ML one. Oops. And then there's the RL one. So I'll link this one. It should work on continuous control mostly. How the hell are there completely different algorithms for continuous control and for discrete and multi-discrete actions? That just means we've messed up massively. Hey, Jess. If I knew, then I'd solve it. Well, what do you think I'm here doing, right? Jess, today I'm kind of going back to basics, trying to figure out some fundamentals on the math. Is there code on this? Yeah. How much data reuse do they do? You beat the odds of roulette using RL. It's a pure game of chance. I don't know how you would. No, right? It's a pure game of chance. Unless there's like a defect with it. But yeah, no, it's the whole point of that is that you can't. For dot train. Oh no, because it's fundamentally not a solvable problem. You try to optimize the distribution given the fact that the rewards optimal and dual problem to the original one. Okay, cool. So why do the results suck on the benchmark that Google is known for pursuing the most aggressively? Like, I'm not gonna go like spend 2 days reading a giant block of math if they don't have results. Like, they don't even have results on the benchmark that they themselves are using the most of the time for everything. Like, I honestly, the control results in my mind are less useful. Too many benchmarks. They're too slow. They're not competitive. I guess the Majoko ones kind of are, but like, I'd rather see the game ones. Continuous optimizers. Why should you have a different algorithm for continuous actions? That's insane. These are like not fundamentally different things. What's your education? From where did you do? Bachelor's in CS at Stanford, PhD at MIT. Finished that a year and a half ago. Now I work on this. Oh yeah, technically you get a master's. I technically master's as well during PhD. We designed for continuous, but it'd work with discrete. Well, then why didn't they tune it for that? There shouldn't be a design for continuous thing. Like, I honestly, which of these two seems more likely to you, right? That, like, the algorithms need to be completely different for continuous or discrete, or that a bunch of researchers over optimize the crap out of an algorithm for one specific set of problems, and that everything is super brittle, so we actually don't know what's even good anymore. I can tell you which one of those two is more likely based on my time in this field. Thank you, Janelle. Yes, you're right. Yeah, that's the problem, right? But that's not what I'm interested in, right? I'm not interested in, like, let's over-optimize the crap out of an algorithm and publish a paper. I'm interested in how do we make this field actually work and not just be a disgusting mess. Steve Brunton? YouTube content. That's cool. They're really good. Yeah, but, like, we're not gonna, like, go say, oh, you have a paper. I'm gonna go spend the next however long implementing it, so maybe it can be good, right? Mechanical engineering? Yeah, mech engineering is cool. Any of, like, the real engineering disciplines are good. Is this just in the paper somewhere? Because I can't find it in the code. Xavier Stokes using RL. They're applications, but not precisely that way. Just so you can solve some of these problems, RL can, it will change. Yeah, it's a really major thing. Paper solves the same problem as VMPO, but with offline data. Is that MPO that you're trying to link? I looked into MPO as well. And do they have indices? Patient. Okay, so this is... Oh, this is massively... See, this is like literally in the last little bit of the paper, you get the bullshit. Do you see? So this is advantage weighted regression, Jess. So this is the thing about all these frickin' papers, is literally, look at this. I have to go to the second to last page of this paper to this like little thing at the bottom to see. At each iteration, the agent collects a batch of approximately 2,000 samples. Okay? Updates to the value function and policy are performed by uniformly sampling mini batches of 256 samples from D. Value function is updated with 200 gradient steps. So that is 40. Wait, hang on. 250. Yeah, 40,000 samples. And then the policy is updated with 1,000 gradient steps. So this is like 100-fold sample reuse. They're doing 100-fold sample reuse. And then they're like, oh yeah, but we beat PPO. DeepMind tries to solve navigation. Oh, that's cool. I didn't know that. Do you see, though, how it's like, how bullshit it is? This is the whole state of the field. At least this one I know what to look for. Oh yeah, this is the repo paper, right? Pathwise policy gradients. Yeah, I never understood this thing. So this thing is just like poor... Like, this is not the problem at all. Like, that's actually something you just solve with the optimizer. I think we grabbed HL Gauss from this and, like, tried to get HL Gauss. And actually, it didn't even do much on Puffer. Maybe it will. Spencer's still looking at that. What are your criteria for a good paper? Actually fucking works. They're flags I look for like, things that are hidden. Misleading comparisons. You know, things buried in appendices. Clever ideas over anything practical. Like, the thing is, a lot of these papers you don't know until you've done a lot of follow-up work. Like, this is a good paper, right? Like, Schulman's papers are the ones that actually work. PPO actually works. Generalized advantage estimation actually works. It's all the same stuff as that offline RL and MPO. Probabilistic inference. What, the advantage? Oh, repo? And so many people have tried it. What? Repo? Hang on. This one? No. Where's this thing? You linked it anyways. Yeah. Oh, it's Peter's, not Sergey's. Cool. Same thing. Formulate RL as the inference. Wise policy gradient. Oh, okay. Actually, this does have at least good coverage. Let me look. Okay, so long bootstrap is mandatory, as far as I'm aware. I'm looking. $15 to $17. Hang on, let me get there, or it's not going to mean anything, right? Brad Q. Brad Pi. Okay, this one we don't need. Wait, TD lambda? Oh, are they calling multi-step TD lambda? Yeah, so this is like, JE fits this, right? Closely related to yes, exactly. Efficient one-pass algorithm is just reduced. Yes, okay. Vantage function and the state act. Oh, okay, because they're gonna take a gradient of this instead of using, okay, fine. Includes advantage estimation is good. Okay. This doesn't solve the, I mean, this looks like it's possibly, like, this is possibly an on-pol improvement, right? But this doesn't solve off-pol at all, right? Like, this does not solve off policy at all. To be fair, I don't really necessarily know. I guess I haven't actually tried with, like, reinforce. The problem is, like, the base methods are so bad. Like, what happens if you just do reinforce with off-policy data? Like, just totally off-policy data? Does it not work? So, the thing is that Levin says it won't work. Where? And does he have experiments? So here's the other thing that I'm realizing is a conflating variable here, right? The key thing that makes on policy actually work, not just like a bit, but to work really well, is generalized advantage estimation. And pretty much any form of this is going to have a value function trained, right? And the thing is, if you're training a value function, you can't train a value function on past data, right? Like, the value function is... the value function's also linked to the current policy. And that one is, like, not, like, questionable from the form. That one just straight up is, right? Like, if you train the value function on the wrong data, you're not estimating the value under the current policy, you're estimating the value of, like, something stale. Maybe that's what we should do, right? Maybe we should, make a version of Puffer where we can play around with the buffer and without the value function in the mix. We should be able to try that, right? So basically, we can separate out generalized advantage estimation and such. We can just end up with discounted rewards or whatever. What does this reduce to if you do... That makes sense to do that. I mean, what's the objective? Well, at least we would be able to see if under this weaker setting, we're able to enable, we enable data reuse, right? That would shift the burden from making policy gradients work to just making advantage estimation work, right? Making advantage estimation work could be substantially easier. Yeah, actually, I think that we have... I could... If I can make the vanilla policy gradient formulation work, I'm pretty confident I can modify advantage estimation. So I guess that's the big question, right? It seems like the on-policy assumption just seems so wrong and weird to me, right? Because, like, yeah, you write out the objective in a way that obviously depends on the current policy, but then the final result is literally... It's the behavioral cloning objective weighted by return, right? Alright. Let me use the restroom real quick. It's only 3. This shouldn't take me very long to do. Grok, is this true? Don't ask Grok. Grok just encodes the biases and stupidity of everyone anyways. Like, it's way better to just try this stuff. Grok will just write you pages and pages and pages and pages of garbage. I'll be right back. Why I see DQN anywhere? No, DQN is like an awful algorithm. You might see variations of DQN. If you actually see like original DQN in production, it's because people are trolling. Nice and easy. Nice and easy. Put here. Right, so this was the version that I made. I gotta reboot the container real quick. Here's your on policy training. Now we need to do quite a bit of modification. So this still works. We need to now make a heck of a lot of changes here. Newest off policies. See? No, it's just one of the more used ones. How's your search went? Yeah, most of the algorithms are just really stupidly slow is the problem. Like, the graphs on paper never actually show you the wall clock time. So it seems to me like a lot of the off-pol algorithms are just way worse than the on-pol algorithms. And, like, to get the same amount of performance, you need way more compute regardless of what you do. And they get better with more compute than on-pol, which is the main appeal. But, like, it's not like they're just better overall, right? There's this huge gap in compute required to get them to work. And they don't scale well with data a lot of the time either. They scale a lot better with the compute. Technical reason. My best guess at the moment is because they use a very short bootstrap, like a 3 or a 5-step bootstrap, where typically in OnPol we're using a 32 or 64-step bootstrap. And the reason for that is because the bootstrap kind of assumes on policy. So in off-pol, you can't really bootstrap over that sort of horizon without importance sampling, and importance sampling just prevents you from using your data. So it's a pretty detailed, algorithmic limitation. Still works. Any paper for research? Well, that's the thing is like the evidence is so poorly controlled in a lot of these that it's not like, oh yeah, they're new ones, they're just better. It's like they're new ones that are better on paper and to be determined if they actually freaking work. I guess Beyond the Rainbow is like one of these niche papers I saw that's like a rainbow with even more stuff bolted onto it that looked decent enough. And like it looks like relatively well done, but the method just gets very complicated at some point. I I kind of fundamentally don't know if I like off-pol without solving that bootstrapping problem. Like the methods are really messy as well. Like on-pol methods are actually pretty clean. Like you can do a lot of damage with a pretty simple algorithm in on-pol. And like you're also just better in a lot of ways that you can't match outside of it. Oh right, this is gonna be a problem, isn't it? How does one do? Without having the value function at the end, how the hell do you do this? I think working on control theory and RL is considered rational. In robotics, absolutely. It's mostly roboticists. So, I mean, it depends, right? How much do you like robots? Pub and RL been gone for a week. I got some world model stuff working, and I think that if you're gonna spend a lot of compute, it's a sensible approach. I don't know if it's gonna be the thing. Well, I don't think it's gonna be the thing that gets you like smooth scaling from high compute to low compute. In robotics fields, more sample efficient, safer with control theory. That's more questionable, I would say. I have to not mess up this calc. Before PPO was our gold standard. There really kind of wasn't one, and PPO was the first like good stable thing. I guess like A2C or something. It was basically PPO without clipping and advantage estimation, which is just distributed reinforce, which is not good. It's kind of like saying like, oh, well, what like PPO is really the first gold standard, and it's stood the test of time. It's like actually quite difficult to improve it. I mean, we've made some small improvements to it, but it's a pretty good baseline. Hello, Aziz, welcome. This is a fine basic discounted return, right? 1 gamma return. I think this is fine. No, I'm doing some other stuff now, Aziz. This is the problem, is it's quite difficult to even, without a value function, it's quite tough. I mean, I guess I could just do... Oh yeah, and you're not even gonna train. Damn it. Papers and merging models. Yeah, you can. But I don't know. RL has, like, more pressing issues, I think. That actually kind of works. That's funny. Not well, mind you. kind of forgot about this problem, right? Yeah, that's rough. Okay, but I mean, there's still stuff we can do about this, right? I think there's still stuff we can do here. Maybe we don't... Okay, maybe what we do, we leave this thing. Maybe we leave this thing alone. Okay, so here is policy. Slightly larger. So we'll do 4 times. Okay, that's the same thing as just not doing any of this. Oh, and then this is actually kind of too big. There we go. A more reasonable size. Does it work? Thing. The problem here is that this policy is not good enough for us to actually play with in any meaningful way, right? Just the depth. Just be the depth, right? I doubt it. Probably just that it doesn't have frame stack or anything like that, right? Really needs the LSTM. That's tough. Yeah, we're really like optimized to having this memory unit. But this memory unit causes other problems. Some sort of simple model I could throw at this. Not really, right? Can't really do this either. I guess we have to stick with this stupid thing, huh? No. Not good enough. I wonder to what extent you can just, like, retune. Hello, welcome. Oh, you can just retune. Okay, so maybe it's worth just having, like, a tuned run with this. I need some sort of reasonable starting point for this. Okay, so no, it doesn't. It's about the best you can do. You can ask a long question, sure. I'll answer what I can. What the heck just happened? Unlucky. Okay. Okay. So this should hopefully be enough. Beep it. I actually did that at one point at OpenAI. You can kind of just like write down the transition matrix for simple enough environments as a sanity test when your algorithms suck. There we go. Let's see if this does anything. You just run a quick sweep, see if it discovers a decent enough policy to be usable. Right? 4 p.m. almost. So the idea of this is if I at least can get a reasonable enough policy, I should be able to separate the value function learning from the policy learning, and I should be able to test replay buffers, right? Yeah, that makes sense. Now the question is whether this learns anything or not, and if it doesn't, then I'm going to need to do... I'm probably going to need to do some more work to make that representation, like, usable. No, that's not mine. That's going to take a while to run, though. Let me see if this process makes sense in the meantime, right? So the idea I have here, the reason we have to take the LSTM out is because the LSTM state gets messed up on every update. So that's just one source of error to remove. Or like one source of possible additional like error to remove. We separate the value and policy function so the representations are disentangled. And then what we can try to do is we can try to apply a replay buffer to the policy learning while keeping the value function learning while keeping the value function learning to be on policy. Oh, and then the value function is wait, when I say to keep the value function learning on policy, does that make sense? Yeah, the value function has to learn from segments that came from the current policy. Oops, here's just kidding. Bigger question. Let me look at this. I've been looking at RL and AI training methodologies in general, trying to get a gist from first principles, which led me to algorithmic information theory, homograph complexity, which seems to be a lot of the origins of the core concepts of general problem solvers. Occam's razor approach seems to fall play from local minima. From there, it seems like the idea of having equal training rate across models yields itself to getting out of those holes, but freezing subsection. Where we count the memory space is trivial. What? All decreases dramatically. The last thing is it isn't shrinking structure. The hash map is actually less complex. Makes sense. Yeah, I think you're getting into a lot of formalism that's like interesting ideas, but not actually the underpinnings of how this stuff works. You're not like you're just looking at most of supervised learning these days at the least. You're just looking at compression. That's all you're looking at. You don't need to go for Kolmogorov, like an uncomputable measure of complexity, or like think of the model hashing stuff or anything like that. Um, you just have a large over parameterized network that is attempting to compress data, which naturally tends to find disentangled representations. We have good evidence of that. And local minima turn out to just not exist in high dimensions. You have saddle points, which is why you need momentum of some sort in your optimizer. You have poor conditioning, which is why stuff like muon is great. But that's it. You don't actually have local minima. Local minima occur in low-dimensional spaces, such as the behavioral spaces of a policy in RL, but that is different from there being a local minima in the optimization of weights. And we do find that models tend to produce compressed representations. That was like a somewhat related answer to your question, I suppose. What would be better for training? Like a checkpoint system or just random? For the quadruped or random? Are you trying to do goal conditioned? Otherwise, like, the thing just has to move in a direction. It's just trying to move forward at as fast as possible is the initial task. It should have, like, local observations anyways. It probably doesn't get absolute position. I mean, so you can just, like, reset it. You can just translate it back to the origin when it gets too far away, and it's not going to know the difference, right? Does that. It runs forward, so what are you trying to do next? That was pretty quick for knocking together a quadruped sim. Suppose you repurposed some of the robotics, or the robot arm at least. Move around 3D space. What do you mean learn to move around? You need, like, terrain? Then you would generate, like, a terrain map, right? And have it walk over that. Look into XLSTM. Yeah. Um, when I originally looked at it, it had absolutely no practical value to me. Now it might have some practical value. But, like, not necessarily on the reason stated in the paper. And there are some considerations as well. Do I want to just tolerate the... I want to tolerate the LSTM drift. It shouldn't need... I guess it does need 1 frame of memory, right? Can I hack that real quick? Ah, shoot, you can't even do this way, huh? Okay. Is there any env I can do where you don't need... like Tetris or something, maybe? $2048 would be good. Triple monitor setup with stream TFT and VS Code. I don't know how you get anything done on that. I'm sorry, I'm new. What is this you're working on? So currently I'm working on some experiments to isolate the effects of off-policyness in the algorithm. What are some paper authors who generally do good work that you'd recommend? On-pol algorithm side would be Schulman, like source creator of CleanRL for his blog post on it, Costa. I mean, I have a list of papers in my my article on X that I suggest. They're big ones. Oh yeah, I mean, I have more papers, like papers, than I have authors, right? Big paper recommendations outside of those in your article, then. I mean, you can look at some of the stuff I've been reading lately, but the thing is, the stuff I'm reading lately is not an endorsement of it actually being correct. It's like mostly me trying to get. I have like a million little pieces of evidence that I'm trying to put together into something that actually works. And like, that's not super satisfying, but that's the state of RL right now. Oh, jeez, this is so slow. I would not suggest doing that, actually. Like, even from DeepMind, the majority of their research is, like, misleading at best, wrong at most. Like, there's no single group that does consistently usable work at all, myself included. This is not Nano, this is Neovim. Why is this by 4? Ew. Weird. Oh. Hmm? Yes. Is this one gonna have the problem of, like, you just being able to do whatever and get some score? The Tetris is way better for this. Yeah, this is better. Is this 0 lines deleted? Yeah, there's some limits. I don't know. DeepMind does a bunch of good stuff. In RL, there's some things about the way that they do their research I'm not a huge fan of. Um, at the least, like right now though, of the big labs, yeah, they're doing the best RL work. I would have put OpenAI over them back in the days of Dota, but like OpenAI just doesn't do it anymore at all. I mean, it's hard to understate. I mean, it's hard to overstate like how good Dota was. Yeah, so this is just straight up trolling then because I cannot get a reasonable policy on this. Right, I can't get a reasonable policy on this, so I think I kind of just got to tolerate the potential LSTM screw ups. So there's no real way around this. Oh, there's money. Not as much, perhaps, but there will be just as much. LLMs are not going to solve everything. Oh. With RL you could solve. I mean, you're still gonna need like supervised learning and pre-training for certain things. It is, I think, generally more powerful. It's again, it's not RL solves everything. It's RL solves interactivity. The pitch. See if this works. Does this seriously not work? No, RL, or do you think? What's a can? Eligma? I have not ever seen that acronym. I've never heard of those. Nope, even telling me what the acronym does not help in this case. I'm gonna do this. Value function needs to be trained separately, right? Would have to be trained. It was supposed to be an MLP replacement. What? Hardware efficient? Not gonna have a replacement for MLPs. It's not hardware efficient. Research hard. And so not sharing the value representation. Really bad. Okay. Throws a wrench in things. I mean, honestly, oh, because you can't move the policy too much because the value function will get stale. Shoot. And there's no way to test this, basically. It's hard. That's very difficult. Okay, so the current hypothesis is the reason that you can't reuse samples is not actually because of the policy. It's because of the value function. Is there a good way to test this? This line of inquiry here is not going to fix it. Get rid of this. Other way I can test this thing really isn't a problem. Isn't there? What happens if they will They should usually give you parameter controlled baselines. Paper. They should tell you how large the model is, number of steps, and a rough wall clock. I had an experiment for this, didn't I? On off Paul. Hmm. You know, I kind of already did this experiment, didn't I? Kind of already did this experiment. It's funny that the best solution I have for this is to go into even higher data regime. On policy just works ridiculously well. Hmm. What to do? The problem is, like, even you're gonna mess up your value function, like, no matter what you do, right? Maybe that's then what we think about. Maybe we think about, alright, to be fair, I haven't really thought about alternate ways of training a value function. Um, Give me a minute, guys. I'm gonna use the restroom real quick and take a minute to walk around, and then I got another 40 minutes or so, today. And we're gonna think about how we can train value functions in a way that's more robust. HTML with reward function. Okay, not really. You can check my RL guide for a lot of content on my thoughts. Be right back. Give me a minute, guys. So here's the question on the math, right? If we assume that I'm correct, and that at least in large part the off-policyness problem is coming from the value function, this here, oh, take a look at this. Infinity, we get, and you add value. So this just goes to discounted return. So this is literally predict discounted return, right? But then it becomes this thingy. I don't know how to think about this sum. I can definitely think about this, though. So that's thinking of value function as predicting discounted return, right? There's no gooning here. We can technically test that with like just very long horizon discounting, I suppose. And then remove the value function entirely. What if we predict average reward? Do anything? It does. Actually, the exponential weighting matters a lot as well. What's the paper today? Several, man. And basically, let me explain. Actually, let's see if this makes sense to you. Let me see if this makes sense to you. Okay, so derivation for vanilla policy gradients. You see here that the formula is set up as an expectation over samples drawn from the current policy. So this is the on policy assumption, right? But the final result, this portion here, this log prob, this is literally the behavioral cloning objective, 1-for-1. And then this is just the return. So the derivation, even though it encodes this on policy assumption into the derivation, the actual solution that you get is literally just behavioral cloning weighted by returns. That doesn't seem to me like this should break if you give it off policy data. Because you're just pushing the probabilities of the actions in proportion to the return. Right? That doesn't seem to have any sort of assumption baked into it as to where the data came from. Now, what absolutely does have an assumption baked in is the value function. Because you never just do this, right? You're always training a value function as part of some advantage estimate. And the value function is explicitly the reward that it's predicting the reward obtained by, or the return obtained by, the current policy. So basically, the question I have here is if we can somehow remove this limitation from the value function, can we use the same core policy gradient algorithm with off policy data? That's what I'm figuring out at the moment. Kind of how I view GSPO. Is this remotely useful for RL? Pretty much, I think that guy, I'm pretty sure that every single importance ratio based metric is bad. Aren't these group methods all, like, based on multiple completions to the same task, though? Moves the value head. Yeah, by doing something incredibly insane, having, like, a ton of completions to the same thing. This would basically, like, doing a state set to, like, the same starting point, right? And then replacing the value function, which you can just have work on an individual sample with, like, a group of 64. This is one of the reasons I think that, like, language model RL is moderately insane, that this is the algorithm that they have. Subject to the same task. Point. Papers weak on math. So I'm pretty convinced at this point that, like, any method that is based on importance sampling is bad. Like, importance sampling just says don't use off-policy data. It doesn't actually, like, correct data, it just ignores it. So importance sampling is you take a ratio of the probability of selecting the action under the new policy and the old policy. So basically, when you get a sequence that has low probability under the current policy, you just don't use it. You don't have enough scale yet? I have more data than you do. You may have more parameters and more compute, but I have more data. Well, what I'm actually trying to do is I'm trying to find a way to enable sample reuse, right? So pretty much I've spent the last 2 weeks on various different methods that promise to make you enable you to reuse old samples, and they all suck. And basically the reason that all these methods suck fundamentally is they don't have the very long horizon bootstrap that you get from doing generalized advantage estimation. I think this is the real on policy assumption, right? I'd be shocked if I were wrong. The advantage calc. Not actually policy gradients, it's the advantage calc. Hard positive and negative sampling. How does that make sense in, like, the type of RL I do, and what does that buy you? I think basically what's going on, right, is that because the trajectory comes from this given policy, then this segment here, or this segment that you're collecting, you're training the value function against it, and that actually does need to come from the current policy. Get enough data to get your model to a point where it can get helpful. You're waiting to get enough data. No, the problem that I have at the moment is there's no way to revisit old data at all. Like, you can get a lucky segment, right? And there's literally no way to revisit it. No, so I have an example where I just give a replay buffer to our algorithm, and I keep in the highest advantage old segments. Only the high advantage ones, mind you. And it, like, monotonically decreases performance even on simple tasks as you increase that buffer size. And the crazy thing about it is, actually, on some of the harder tasks, if you have just a very, very small buffer, you can actually, like, 10x performance early in training. Because you solve the sparse exploration problem with this buffer. Early data? No. Because advantages are actually on policy, right? Advantage is a function of... it's trained on the current trajectory segment. So basically, you're assuming that because you're training on the segment, that's what the policy will produce. Yeah, I know, but basically, so what's happened is, over the last 3 weeks, I have not been able to get a single sample reuse method to do better than baseline under any circumstances. You reevaluate advantage from your... I already do that. I already reevaluate advantage every single time. I guess I haven't removed, like, all the conflating variables, I suppose. I think. Hang on. Got a 32K mini batch, right? I thought about the LSTM hidden state. I don't think that's it. Yeah, literally you give it, it's literally about the same, even a little worse, even with just a tiny amount of data. Yeah, those don't exist. At least not working ones. Oh, actually, if you have the fast slow LSTM is like basically the one hierarchical thing that actually might kind of work. All the other ones are sort of bullshitty. I don't even know if the fast slow thing works. It just might work, you know? Yeah, so what you're predicting is like, let's just get rid of these. You're predicting exponentially weighted average of n-step bootstraps. Tested my network. Almost it worked. 200. It's odd. This one makes sense at least, right? Yeah, this actually makes. This is it, really. You know, I suppose the other thing is you don't get the full estimate, right? You don't get the full estimate for all of your data. You actually, it decays pretty quick, honestly. Like, alright, I hadn't actually thought of that. Is it 0.9? Yeah, so yeah, like Breakout has this tiny lambda. Okay. Do you know, you probably don't even need like a crazy long horizon bootstrap. Do you? Just that the trailing end of your buffer, right, doesn't get the full bootstrap, so you make it longer to average it out. Okay. That's definitely true. What did I miss? Mostly, I think the real culprit is the value function. The value function having to be really strongly on policy. What did I get for, like, neural MMO? We got this, like, really weird set of params there, didn't we? Gonna be crazy long estimate. I don't know, Weston. It's hard to say if you're not on like a mature, well-tested implementation. You're kind of just like wandering around in the dark is the problem with that. Implementing yours. You say you're implementing mine. Are you like putting it into Puffer? Like the best way to do stuff on this is to do like make the minimal possible change to PufferLib to test your idea. Like the only stable starting point. So it's not a crazy long bootstrap, but it's longer than what's gonna get used in off-pol, right? Really. This is really the source of all of our problems. The value bootstrap. Your end was a pendulum. Alright, well that's my signal for today. I got a meeting to get ready for, and then I've got to go to dinner. I will be back tomorrow doing research. I'm not entirely sure what. I'm going to have to think about this a bit and see if I see a productive avenue for this. It's hard. Very difficult. I think I'm at least closing in on the right set of problems, though. Definitely I'm understanding this in a way that very, very few people have put the time into to understand. And backed with a lot of practical results as well. For folks who've been watching me bang my head against this for the last 5 hours, thank you for tuning in. If you're interested in my work, Puffer.ai for all the things. Feed the Puffer a star. Helps me out a lot. Join the Discord if you want to get involved. This is all open source work. It's not all hard research. There's a lot of like fun low-level game dev that actually helps us advance the research. These are all playable online. You can also follow me on X for more reinforcement learning content. I write about my work every so often. I have some nice guides on there, on and so forth. It's been a heck of a long week. A lot of work. But I'm going to get some rest. I'll be back tomorrow. Bye.